So next, we're going to briefly discuss this Laplace equation of continuity. Okay, so first, as I mentioned, this Laplace equation, it describes how head or energy changes as water flows through soil. And so Laplace equation is actually, it's not unique to geotechnical seepage problem. It can be applied to many problems where there's a differential energy across a resistive medium. And a couple more examples I give here include this voltage difference in an electric current or temperature difference in a heat flow. So all these can be solved by the Laplace equation of continuity. And for our problem here, we are interested in this water flow. And so on the right-hand side, you see actually two pictures. So this is a seepage problem. And I will not show, so I'm going to skip the details of the derivation here. It's pretty straightforward to derive the Laplace equation. Basically, if you look at this picture here, this soil element, this picture at the bottom here, this is a small soil element A taken from this soil media here from this seepage problem. And this derivation uses continuity of flow, basically what flows into this soil element A, so that's your inflow, must equal to what flows out, so that's your Q out along X and Z direction. So you use continuity flow and then use Darcy's law, and you can get Laplace equation of continuity. So again, I'm skipping some details here, but it's really very straightforward to derive this. But this is what the Laplace equation of continuity looks like for our seepage problem. For anisotropic soils, where you have different permeability or hydraulic conductivity in the horizontal and vertical direction, X and Z. And this is what the Laplace equation looks like for anisotropic media. And if Kx equals to Kz, if it's an isotropic material, then Laplace equation boils down to this simple expression here. And if you look at this second equation here, you will notice that this Laplace equation actually is independent of hydraulic conductivity. Okay? So the solution of this Laplace equation for isotropic media is independent of the hydraulic conductivity. So it depends on the geometry of the problem, basically. And as I mentioned previously, the solution of Laplace equation is the spatial distribution of head or energy. So that's what you get from solving Laplace equation. So you get the head we call H as a function of location or coordinates X and Z. Okay. So that's the Laplace equation. And to solve Laplace equation, there are three options. And the first one is you can solve Laplace equation using analytical solutions or analytical methods. But analytical method only works for very special and very simple cases, like 1D flow through isotropic media. That's where you can get analytical solutions. And the second type is more general and more accurate method is numerical methods. And one example of or numerical methods is this finite element method. So it's a name for a numerical method. And I included this picture here, this figure. So this is basically a solution of Laplace equation for a 2D flow problem by finite element method. And the color in this figure represents the potential, that's energy H. And the lines here represent equal potential lines. And we'll talk more about equal potential line later. And the third method is actually we're going to learn and use in this chapter. It's a graphical approximation method, and that's called flow nets. So this is what geotechnical engineers use to solve practical seepage problems, flow nets here.